So, in the last video we was determining where hinges occur in beams. We touched upon partial and complete collapse of beams, and we'll be taking this further in this video as we begin to look at portal frames. Before we get our teeth stuck into it, let's just remind ourselves of what the plastic analysis of beams and frames involve. The analysis includes the following: the collapse loads, the number of possible hinges required to induce collapse, the possible hinge positions, the independent collapse mechanisms and their associated MP values, the possible combinations of independent mechanisms to attain the highest required MP value, and lastly, checking the validity of the calculated value with respect to the mechanism, yield and equilibrium conditions. So far we have covered those points in red, and in this video we'll be looking at the points in green, albeit not the whole part of those points. In further videos we can start calculating collapse loads as well as values for MP, but first we need to get our understanding of the subject. So when we do plastic analysis, normally the first step in analysing a structure is to calculate certain values. The first is lowercase m. Now lowercase m represents the number of possible hinges. Lowercase n represents the number of redundancies within that structure. Uppercase N is equal to the number of independent mechanisms. And then lastly, m plus 1, lowercase n that is, equals the total number of hinges required for complete collapse. Once we determine these values, portal frames and continuous beams become much easier to analyse. As we said in previous tutorial videos, hinges occur at positions where maximum bending moments occur. Therefore M can be determined easily enough. The number of redundancies can be found from the total number of reactions minus the equations of equilibrium, and then uppercase N is equal to lowercase m minus lowercase n. Then lastly, the total number of hinges required for complete collapse is just simply n plus 1. If we look at a portal frame then, don't worry if you haven't ever analysed a portal frame before, we won't be throwing any numbers into the problem. This is purely an example for determining m, n and uppercase n, and then m plus 1. Let's just put a few loads on so we can visualise how this frame might collapse. We've just got horizontal load here, which we're just going to call H, and a vertical point load here, which we're going to call V. So, starting with M, the number of possible hinges. The key to determining this is the bending moment diagram. So, we need to think about the bending moment diagram for this structure, and then we know that hinges can occur at, or do occur at, the points of maximum bending moment. Don't worry if you aren't familiar with the bending moment diagram for this structure. We'll be going over that when we look at problems for this topic. But just take it for now, if you don't know, that this is a plausible bending moment diagram for this portal frame. Now, you can see here that we have a maximum bending moment here. We will label this point 1. We have another here, point 2, another here, point 3, point 4 here, and point 5 down here. Now you may be thinking at point 4 here, why do we not consider both of the maximum bending moments? Well, it's because if you look at the location on the bending moment diagram, they are actually the same. So the maximum, although there are two maximums that we can see, they're occurring at the exact same point. Therefore, we only consider them as one. So from this, we can see that our m is equal to 5. Now, how do we determine lowercase n? Well, I said lowercase n is determined by the number of reactions minus the equations of equilibrium. So let's start off with the equations of equilibrium. We have horizontal, vertical, and moments. So we have 3 equations of equilibrium, and that will always be the case. So now we need to look at the number of reactions. So the best way to do this is to look at the supports that we have in the system. If you have a pinned support, you'll have horizontal and vertical reactions. If you have a fixed end connection, you'll have moments, horizontal and vertical reactions. And if you look in our portal frame here, we have 2 fixed end connections. Therefore, the number of reactions in this system is 2 times 3, because we have the fixed end, 3 reactions, moments, horizontal and vertical, so 3 times 2 equals 6. Therefore, our n is equal to 6 minus 3, 3 being the equations of equilibrium, and obviously that is equal to 3. Then we can calculate our the number of independent mechanisms, capital N. Capital M is simply lowercase m minus lowercase n, and so that will be 5 minus 3 equaling 2. The total number of hinges required for complete collapse will be lowercase n plus 1, so therefore 3 plus 1 equals 4. Now we know that 4 hinges are required for collapse in this structure. Let's take a look now at partial and complete collapse. Partial collapse means that the number of hinges formed in a structure is less than the required amount for complete collapse. We can write this as number of hinges formed is less than n plus 1. That's for partial collapse. For complete collapse, obviously at least n plus 1 number of hinges are required to form, and we can write this as number of hinges formed is equal to or greater than n plus 1, and that's for complete collapse. However, for complete collapse, 3 conditions must be satisfied. They are the mechanism, equilibrium, and yield conditions. For the mechanism condition, sufficient hinges must develop, and that's what we're referring to when we talk about the n plus 1. Equilibrium. We're saying that the bending moment for the collapse mechanism must be in equilibrium with the applied collapse loads. Now our systems, the structure is normally always in equilibrium, so we don't need to concern ourselves with this condition too much. But nonetheless, we need to be aware of it. For the yield condition, we are stating that the magnitude of the bending moment diagram, the magnitude of the bending moment on the structure does not exceed MP for the structure. Let's look at a continuous beam then that we can analyse, so we can understand what we mean by partial and complete collapse. So we have this beam here, spanning from A to B to C. We have a point load P and a UDL W. So let's start off by calculating M. If we draw a bending moment diagram, again, the best place to start with calculating M, we can see that we have 1, 2, 3, 4 peaks. So the number of possible hinges equals 4. Let's calculate our N. N equals the number of reactions minus the equations of equilibrium. How many reactions do we have? We have 3 because we have a fixed end here. We have 2 roller supports here. Now there's no horizontal reaction here because they're roller, so they're free to move in the horizontal axis, therefore there's no horizontal reaction, and therefore there is only the vertical reaction at the supports at B and C. So 3 plus 1 plus 1 equals 5, minus the 3 equations of equilibrium. 5 minus 3 equals 2. Capital N, the number of independent mechanisms, equals M minus N. 4 minus 2 equals 2. N plus 1 equals 3, so there are 3 hinges required for full collapse. So let's look at a mechanism now for partial collapse of this continuous beam. So here we know that for full collapse we need 3 hinges to form. So if we have less than 3, we know it will be partial collapse. So in this scenario here, or mechanism 1, this is what an example of what it could look like. We have 1 hinge. Only BC has collapsed, and we know that the number of hinges is less than n plus 1, so 1 is less than 3, therefore we have partial collapse. If we look at another mechanism for partial collapse, here we have 2 hinges, and again 2 is less than 3, therefore it is partial collapse. Now when analysing these two, how do I know where to locate these hinges for partial collapse? Why haven't I chosen any of the other locations? Well, because you need to break this continuous beam up into spans A to B and B to C. And if you look at those bending moment diagrams individually, you'll be able to determine the locations of where I've put the hinges, and hopefully from the bending moment diagrams that I've included here, you can see how I've identified where the hinges go. Now let's look at complete collapse of this beam. Here we have mechanism 3 and here we have mechanism 4. We have 3 hinges in both, therefore it is complete collapse of the structure. How can we determine the actual collapse mechanism of the beam? That might be a question that you're thinking. Using the 3 conditions is the answer. So if we look at mechanism 3 and mechanism 4, is the equilibrium condition satisfied? Yes. Is the mechanism condition satisfied? Yes, we have 3 hinges in both mechanisms. Is the yield condition satisfied? The answer is we don't know. We don't know which one satisfies the yield condition. To determine whether the yield condition is satisfied, we would need to use some values and make sure the bending moment on the structure does not exceed the value of MP, that is the plastic moment of resistance for the structure. So hopefully you've managed to follow, and in the next video we will look at satisfying the yield condition and obtaining values for MP. See you in the next one.